Steam is a wonderful thing. Across the globe, steam is used daily to produce items and services such as heating a room or creating a bottle of bourbon. In this module, you will learn how to increase the efficiency of your steam system, thus saving energy and money. But first, what is steam? Steam is a gaseous form of water. It does not have any color, taste, or odor. Steam is valuable for heat transfer because of its sensible and latent heat properties. Sensible heat is when an item changes with temperature, while latent heat concerns heat exchange occurring during phase change. In other words, heating the temperature of water by 15 degrees Fahrenheit is sensible heat, while latent heat is the amount of heat required to convert a liquid to gas, or vice versa, at a consistent temperature and pressure. Compared to water, the heat content of steam vapor is more than tripled. A BTU is the amount of energy required to raise a pound of water 1 degree Fahrenheit. To raise a pound of water from 32 degree Fahrenheit to 212 degree Fahrenheit would require 180 BTU. Water has a boiling point of 100 degrees Celsius, or 212 degrees Fahrenheit. This temperature can vary with ambient pressure. At atmospheric pressure, the boiling point is 212 degrees Fahrenheit. The boiling point is also a saturation condition. A saturation condition occurs when both the liquid phase and the vapor phase exist at the same time. If a small amount of energy is added to saturated liquid, it turns into a vapor. Likewise, if a small amount of energy is removed from saturated vapor, it will condense to liquid. To convert a pound of saturated water from liquid to vapor takes 970 BTU. To get the total heat energy of steam created from a pound of water, you must add the 180 BTU from raising the water from 32 degrees Fahrenheit to 212 degrees Fahrenheit and the 970 BTU from converting a pound of water from liquid to vapor. The total heat energy in a pound of steam is 1,150 BTU. Let us recap. Steam's total heat content is 1,150 BTU per pound. This is because steam has 180 BTU per pound of sensible heat and 970 BTU per pound of latent heat. Sensible heat and latent heat added together equals steam's total heat energy, 1,150 BTU per pound. Because of its heat transfer properties, steam is often used by industries and manufacturers for mechanical work like running engines or heating processes. Most steam systems are designed in a loop that consists of 4 basic sections: steam generation, steam distribution, heat transfer, and the condensate return. Steam production is affected by several factors. Site-specific variables must be taken into consideration and assessed when determining cost factors that affect steam operation. Key cost factors include fuel, labor and maintenance, equipment, electricity, sewer, water, and chemicals. Keep in mind, site-specific variables are often overlooked or assumed in published efficiency data. On the screen, you can see the average breakdown of the cost factors for a steam operation. At 74%, fuel is the largest cost factor. To generate steam, a variety of fuel types can be utilized. Standard fuels include natural gas, propane, and number 2 to number 6 fuel oils. Non-standard fuels include biogas, landfill gases, waste oil, biodiesel, and ethanol. A fuel analysis must be completed on non-standard fuels used to generate steam. Common solid fuels used in system loops include coal, wood, animal waste, and other biomass crops. We will start the journey of achieving maximum steam efficiency where it is most commonly generated: the boiler room. There are 4 main types of boilers: cast iron sectional, commercial water tube, firebox, and industrial water tube. During this video, we will look at 4 past wetback and immersion designed fire tube boilers and will try to put into perspective real-world applications of both combustion and boiler efficiency. Natural gas is emerging as an ideal package of cost-effective, reliable, widely available, and reduced emissions fuel. Note the United States has become the largest natural gas producer in the world. For this presentation, we will be using natural gas to base our discussion. When it comes to steam efficiency, the first condition to be evaluated is combustion efficiency. Combustion efficiency of a boiler is the burner's ability to burn fuel. In other words, combustion efficiency measures how effectively the heat content of fuel is transferred into usable heat. The two parameters which determine combustion efficiency are unburned fuel quantities and excess oxygen levels in the exhaust. Operating a boiler with optimum amount of excess air will minimize heat loss up the stack and improve combustion efficiency. The stack temperature and the flue gas oxygen concentrations are primary indicators of combustion efficiency. Given complete mixing, a precise amount of air is required to completely react with a given quantity of fuel. In practice, combustion conditions are never ideal. Additional or excess air results in unburned combustibles and causes heat loss due to increased flue gas flow, thus lowering the overall boiler fuel to steam efficiency. The table on the screen relates stack readings to boiler performance. A typical low fire setting uses 40% excess air and results in 6% oxygen content in the flue gas. A high fire setting uses approximately 15% excess air and results in 3% oxygen contained in the flue gas. On well-designed natural gas-fired systems, an excess air level of 10% is obtainable. The lower the percentage of excess air equals a higher combustion efficiency. An often stated rule of thumb is that combustion efficiency can be increased by 1% for each 15% reduction in excess air or 40 degrees Fahrenheit reduction in stack gas temperature. Imagine you have two boilers with a stack temperature of 400 degrees Fahrenheit. Boiler number 1 runs at 5.5% oxygen with an 81.2% combustion efficiency, while boiler number 2 runs 3% oxygen with an 82.3% combustion efficiency. Boiler 2 has a greater combustion efficiency by 1.1%. Both boilers operate at 400 horsepower for 4,380 hours per year at 50% fire rate. A therm is a unit of heat that is equal to 100,000 BTU. If it costs $1 per therm to operate the boilers, boiler number 1 would cost $722,203 per year, and boiler number 2 would cost $712,550 per year. Thus, to operate boiler number 2 versus boiler number 1, the annual savings is $9,653. Over the 40-year life expectancy of the boiler, the savings would be $386,120 at 2017's fuel costs. Remember, this savings is from just a 1.1% increase in combustion efficiency. Little things can make a big impact. For example, air temperature can affect combustion efficiency in air requirements. As air temperature drops, air density increases, and vice versa. Air density can adversely affect the excess air on a burner. Therefore, constant monitoring is recommended. Technicians will set the burner slightly lean to make up for this and to help ensure the burner does not soot. Soot has 5 times the insulating value of asbestos, so an eighth of an inch of soot results in a heat loss of 47%. Thus, an eighth of an inch of soot will increase fuel consumption by 8.5%. This lean setup does not replace monitoring. Monitoring in control systems like flue gas analyzers and oxygen trim systems can help you maintain optimum excess air levels and achieve consistent efficiency. Flue gas analyzers monitor the composition of flue gas, thus identifying energy loss trends and providing early warning of control failures. In an effort to maintain optimum levels of excess air, flue gas analyzers give information which allows data to drive decision making. Oxygen trim systems continuously monitors the excess air levels in the stack and provides a signal to the burner controls. thereby automatically maximizing excess combustion in air and optimizing the air-to-fuel ratio, which typically results in an additional 2 to 3% fuel savings. Boiler efficiency is measured by fuel-to-steam efficiency, basically BTU input versus BTU output, ultimately reflecting the amount of heat transfer from the fuel source to steam or hot water. Fuel-to-steam efficiency is a better measure of overall efficiency because it takes into consideration the effectiveness of the heat transfer, as well as the radiation and convection losses in the boiler shell. Published efficiency is based on 100% of the boiler's rated capacity in a steady state and often does not take into consideration cycling and purge losses, along with other operating variables by application that will reduce actual efficiency. It is common for stated boiler efficiency to be less than combustion efficiency. It is a general observation that boiler efficiency tends to decrease as the boiler load decreases. Both practically and theoretically for any boiler, the efficiency is highest at maximum load conditions. At part loads, a considerable drop in efficiency is noticed. Given the lower efficiency and low fire, it may be more efficient to shut the boiler off if the boiler has a rapid response to load demands. However, make sure to take warm-up losses and thermal stress into consideration before shutting the boiler off. To ensure that your boiler operates at high efficiency, it is best to operate at full load conditions. Warm-up losses are the losses associated with the time and fuel required to heat a boiler from cold start to steam. Remember, labor hours must also be considered into warm-up losses. In a single-pass immersion tube boiler, each tube absorbs the same amount of radiant heat because a flame directly heats each tube. By flaming each tube directly, warm-up time to steam from 50 degrees Fahrenheit water is often less than 20 minutes for boilers of all sizes. In a traditional multi-pass shell design boiler, one large diffusion flame within a furnace tube indirectly heats all the tubes. This creates a large temperature differential which causes constant thermal stress. By indirectly heating all the tubes, warm-up time to steam from 50 degrees Fahrenheit water is often 4 to 8 hours, depending upon the size of the boiler. When comparing the annual boiler warm-up costs between an immersion rapid response boiler and a multi-pass boiler, the immersion rapid response boiler costs $16,319 less than the multiple pass boiler. Over a 30-year service life, the total savings would be $489,571.88 at today's fuel costs. During startup, the burner does not start firing immediately. Instead, it purges air before actual atomization. The purpose of the pre-purge is to blow away the residual exhaust flue gases that stayed in the furnace and the boiler tubes while the boiler was shut down. Similarly, a post-purge cycle is carried out after shutdown. These purging cycles blow away hot flue gases, which is a loss known as purge losses. On the screen is a comparison of purge losses between an immersion boiler and a multi-pass boiler. As you can see, the immersion boiler's purge losses are around 13,000 BTU per hour, while the multi-pass boiler purge losses are closer to 76,000 BTU per hour. This is a difference of roughly 63,000 BTU per hour. Over the course of a year, the multi-pass boiler's total purge losses could be more than 125 million BTU greater than the immersion boiler. Another item to consider when looking at boiler efficiency is standby losses. Boiler standby loss is the energy lost when a boiler is in the off mode. This energy will need to be made up when the boiler is back online. Typically, efficiency losses range between 0.3 and 2%. Many variables can contribute to the decreased efficiency caused by standby losses. Two such variables include the temperature and the air movement in the boiler room. However, remember, the larger the pressure vessel, the greater the standby loss due to the surface area of the boiler. Standby losses can also be affected by the boiler design. A dry back boiler with a large refractory rear door will lose more energy than an immersion or wet back boiler. Ancillary products are support equipment that can increase overall boiler efficiency. In this module, we will discuss deaerators and stack economizers. A deaerator is a system that is used to remove oxygen and other gases from water fed to steam generating boilers. This system increases efficiency and protects the boiler. A deaerator consists of a storage tank, a heating apparatus, feed pumps, and water level controls. A deaerator works by raising the water temperature above the zero saturation temperature. To overcome surface tension, the water is agitated and then atomized to the smallest possible droplets. This frees non-condensable gases like oxygen and carbon dioxide, which are vented from the system. This process also heats the feed water. Heat in the feed water increases boiler efficiency by 1% for every 10 degrees Fahrenheit. For example, if a typical condensate at 180 degrees Fahrenheit is increased by 47 degrees Fahrenheit, this will equal a 4.7% efficiency gained. Mechanical deaeration provides a fixed method of eliminating oxygen and other gases. The only other method is to inject high volumes of an inexpensive scavenging chemical into the boiler feed water supply. A fixed method, like a deaerator, lowers operating costs. Stack economizers increase efficiency by utilizing stack losses, taking advantage of lost flue gases and raising boiler feed water temperatures, thus acting as a boiler efficiency equalizer and increasing fuel savings up to 8%. Installing insulation can increase efficiency by reducing heat loss during steam distribution. When installing insulation, make sure the insulation fits correctly and can withstand the conditions. If insulation is ill-fitting or cannot handle the environmental conditions, it will be ineffective, thus reducing efficiency and increasing operating costs. Another item to consider is if the insulation can be easily removed and reinstalled. If removed insulation cannot be reinstalled or is difficult to reinstall, most facilities will opt for buying and installing new installation, which increases the facility's waste and financial costs over time. Opportunities for increased efficiency can be identified by performing an installation audit. This process properly identifies items which were overlooked during the initial installing process. An installation audit will provide a detailed report of items to be installed along with a description of the location and corresponding savings. A steam trap can be used to assist with efficiency during steam distribution. A steam trap is a self-contained automatic device that opens to remove condensate and closes to live steam. There are three main types of steam traps: thermodynamic, mechanical, and thermostatic. Steam trap types vary based on how the valves operate. Thermodynamic steam trap valves are operated by steam flow, while mechanical steam traps use the difference in density between steam and condensate to operate the valve. Thermostatic steam traps sense temperature change to operate the valve. You might be wondering, what must a steam trap do? The key items a steam trap must do includes removing condensate as it forms and removing air and non-condensate as it collects. Other factors to consider when selecting a steam trap include its ability to handle dirt and pipe scale, resist destructive freezing and water hammer, plus handle modulating pressures and varying condensate loads. A steam trap should perform all these tasks while providing a long, energy-efficient service life. Steam traps are important because they maintain steam distribution by removing condensate. Properly sized and properly operating steam traps maximize the efficiency of heat transfer equipment. Undersized or failed closed traps back up condensate, which leads to poor steam quality, reduced heat transfer, corrosion, and water hammer. Failed steam traps waste valuable energy dollars. Steam traps should be tested periodically to reduce the cost of failed steam traps. The recommended testing schedule is based on the amount of pressure a steam trap handles. High pressure and critical steam traps should be tested monthly. Medium pressure steam traps should be tested twice a year, while low pressure traps can be tested once a year. It is recommended that all steam traps be located, tagged, tested, and recorded in a data sheet to facilitate the ease of future surveys. Training for maintenance and survey personnel is critical for the success of in-house programs. A closed-loop system which collects condensates is advisable for energy efficiency. Condensates collected in the return can be used again within the steam loop as feed water. Thus, the collected condensates will supplement water use, which will increase water efficiency while decreasing the water bill. Condensates require less heat or energy to boil, which will reduce the system's energy consumption and fuel costs. Collected condensates will also require less conditioning chemicals than water, which saves money that would normally be spent on conditioning chemicals. Recovering condensates not only increases the steam system's water, energy, and chemical use efficiency, but saves money. There are many ways which you can save energy and money through steam efficiency. Equipment is only roughly 10% of the total cost of a steam system, while more than 70% are related to fuel costs. Thus, increasing a system's fuel efficiency can save you money. When looking at a system, remember, a steam system's efficiency cannot be measured just by looking at published data, which is measured at 100% firing rate at a steady state. Site-specific variables must be considered. It is important to know that combustion efficiency is not the same as boiler efficiency. Combustion efficiency pertains to the burner, while boiler efficiency relates to multiple factors in boiler design and is measured by fuel to steam efficiency. Both play a big part. A 1% increase in combustion efficiency can add up to large saving. Boiler designs affect the equation in the form of standby, purge, and warm-up losses. Items like control systems, ancillary products, steam traps, and insulation can provide increased efficiency. Do not forget any maintenance requirements and costs. Proper maintenance will increase steam efficiency and will be around 10% of the total cost. Lack of maintenance can lead to failed products as well as dangerous conditions. Keep in mind, different boiler designs can have different maintenance requirements. Staff should be trained and licensed for the equipment so it can be operated in the most efficient manner. We hope after spending the last 20 minutes or so with us, you have walked away with a variety of methods and ideas to increase your steam efficiency and save money. This module has been brought to you by the Kentucky Division of Compliance Assistance within the Kentucky Department for Environmental Protection in partnership with the Kentucky Pollution Prevention Center. If you would like information about Kentucky Excel, Kentucky's Environmental Leadership Program, please visit our website on the screen. We would also like to invite you to join the Kentucky Excel community. Please share with us your steam efficiency stories by using hashtag KentuckyExcel or tagging the Kentucky Division of Compliance Assistance in a Facebook post. Thank you for watching.